this morning. This is the CCI Computing Faculty Seminar Series, our third and last of this term. This morning we've got a new member of the computing faculty, Dr. Geoffrey Mainland. I'll let him introduce himself, and he'll tell you about the important facts and figures of his background.
So I'm brand new. I just started September 1st, joined the faculty of Department of Computing. Before that, I was at Microsoft Research, Cambridge, UK, doing a postdoc. I work in programming languages, which is really about reasoning about programs. And I'll tell you a bit about my work this morning. So I'll be talking about high-level Haskell, translating high-level Haskell to efficient low-level code. So there are kind of two take-home messages I want you to come away with today, which is that we don't have to sacrifice efficiency necessarily to use high-level languages. And also that high-level languages can actually make using specialized hardware easier, to make it easier for us to do our jobs as programmers. Okay. So what do I mean by low level? I'm really talking about low-level hardware here. So some examples are Tesla's K20. This is a member of NVIDIA's newest generation of GPUs. So this is a graphics card without a graphics display. It's compute only. For certain types of parallel computation, these devices are great. But you have to learn a lot to be able to use them efficiently. So you need some low-level knowledge. You need to learn a new language, etc. This is a Sora radio control board from Microsoft Research. It's a software-defined radio platform. So software-defined radio is something I'll talk about in a few more slides. This lets you experiment with new radio protocols. So really it lets you implement new radio protocols in software rather than in hardware. So you can imagine it's a great platform for research and development radio protocols. This is the Net FPGA 10 gig. I have two of these coming from an equipment donation, so I'll be playing with these soon. It has 4 ports here, 4 10 gig ports. It has a Xilinx FPGA here. Actually, the Sora radio control board has one also, so these are bits of programmable hardware. And just like the Sora radio control board lets you write new radio protocols in software, the Net FPGA lets you write new routers, for example, in software, but have them operate at 10 gig line speed. So this is another great platform for experimentation. It lets you write these protocols in software and run them at basically line rates. So these are all specialized hardware for pretty specialized tasks. They're all fairly difficult to program. And the knowledge you gain learning to program one of these systems doesn't really transfer to the other systems. So one thing I'm concerned with is how can we make these devices easier to program? And I could add another bullet point here. And how do we potentially capture the abstractions that are common across these platforms in a language so that you can reuse some of that knowledge that you gain, say, learning to program a GPU to program these sorts of devices. There are some similarities in the way you program these guys. But you currently have to use completely different languages and environments to actually use them. Now, I want to make it easier to program, but I don't want to give up too much performance. So getting a little bit of performance is okay. It's a good trade-off if it's 10 times easier to program if I lose 5% performance. But I don't want to completely give up performance. So you always have to have that in the back of the mind. So why Haskell? Well, what is Haskell? Haskell is a language, a programming language. I'll tell you a little bit about it. So why Haskell, from my perspective? Well, it's pure and functional. Okay, what does that mean? I don't want to get into philosophical debate about what a functional language is. So I'll say I think it's a pretty acceptable general definition. In a functional language, the functions you define act like mathematical functions. So you give them the same input, you'll get the same output. So take sine function in C, right? You call sine with the value 2 pi, you're always going to get 0 back. That's not a property that's true of all functions you define in C. Because your function may do some things under the covers, it may go bang on some global variables, it may output something on a terminal, etc. So functions are not pure language like C. Well, let me dive in a little bit deeper with just a couple examples. So this is just Haskell code. Don't worry about it if you know Haskell. You don't know Haskell. This is a type signature. So the left hand here I have main. This is like main function in C program. Double colon, you can read that as has the type. So we're saying main has the type IO unit. You can think of this unit as void in C. So what are we saying? We're saying, well, main is some sort of computation that happens inside this IO thing. So it's actually a pure function, but it's going to happen inside IOs. This type signature is telling us something about the function. This might be a little clearer if I show you this type signature. So this is ID. Think of this as identity. And there's an implicit quantification here. So it says ID has a type A to A. There's an implicit quantification that says for all A. So for all A, ID has type A to A, which means I can take any type I want, for example, integer, and plug that in for the two A's. So what do you know looking at this type signature about the function? I haven't told you what the function does inside. I haven't shown you the definition. But in fact, just knowing what this type is, you already know a lot about the function. Now Haskell's pure, so ID is not going to do anything under the covers. It's not going to bang some pointers or print something out, etc. So with that hint, can you tell me, what do you think ID is going to do? If I give you an argument in your ID, what is ID going to do with that argument? It's going to return the argument. It couldn't possibly do anything else. So there's only one thing, actually there are two things in Haskell ID could do. The other thing ID could do is not terminate, so it could loop forever. But if it returns something, it's always going to return the thing you gave it. So why am I telling you this? It's silly, right? The point is that you can tell an awful lot about a function just by its type. Not only can you tell a lot about a function based on its type, but the compiler can tell a lot about a function based on its type. If you had a similar function in C, or even a language like ML, which is functional but not pure, you wouldn't know that if I gave ID a value, it could only return that value. So in a language like ML, which is still functional but not pure, it could still bang some references or do some other side-effecting things under the covers. So the type in a language like ML does not tell you as much as the type tells you in Haskell. So this is really why I think purity is important and why Haskell is a good language. So also, when you think about parallelism, what 20 years ago, people thought that pure languages would be great for parallelism. Because, okay, so I look at this function, I can tell it's pure, it doesn't have any side effects. If I look at 2 bits of a program, and they're both pure, I know, well, I could potentially run these in parallel, because they don't interact in any way. So that purity tells you something about the program, namely that 2 different pieces don't interact, and could potentially be run in parallel. Now, this didn't quite pan out, because the remaining question is, how do you actually partition up all these potentially pure things? Where do you insert the parallelism? So that's really a problem. But still, purity gives you a good handle on solving these sorts of problems. And often solving the problems automatically inside a compiler. So implicit in my explanation of why Haskell is important here is that it has a strong type system. So that these types are actually informative, and these types can capture a lot of invariance about the program. Just from an implementation perspective, Haskell also happens to be a pretty good platform for embedding new languages. So you can take a language and kind of embed it in Haskell. So you reuse Haskell's syntax, you reuse the type checker, but you get kind of a whole new language out of it. So you don't have to re-implement all that stuff yourself. I'll talk about that a little bit more, but it's kind of technical and not super important for the presentation. That should say good. It has a good implementation in active community. That's also important. So with that said, let me just kind of give the outline of the rest of my talk. It's going to be based on kind of current and some past and future work. So I'll talk about answering this question, can high-level languages be efficient? And that's based on a paper I presented this past September with some colleagues, Roman and Simon. Simon's at Microsoft Research. It's exploiting vector instructions with generalized tree diffusion. And I'll be talking about whether or not we can use these high-level languages to program low-level devices, including GPUs. And some work that was just submitted is using functional languages to program software-defined radio platforms, so creating these SOAR platforms, and that's joint work with people at MSR and also at Princeton and UIUC. Then I'll talk a little bit about future work, focusing mainly on software-defined. Okay, so exploiting vector instructions. Okay, what's that mean? These are 3 questions I would expect you to have. So what are vector instructions? Why are they useful? Who cares? And what do you mean by exploit? So processor families like Intel is added to the x86 instruction set. Maybe you've heard of SSE instructions, AVX, AVX2, AVX 512. These vector instructions let you operate on more than one thing at a time. So operate means you can do things, typically mathematical operations, addition, subtraction, division, take reciprocals. And thing is typically a floating point number, single or double precision, or an integer, 8, 16, 32, 64 bits. So you can operate on multiple bits of data in parallel at the same time. So why is this useful? As you might expect, if you can make efficient use of these instructions, it really speeds up your code. Because instead of doing one thing per however many clock cycles, you're doing 2 or 4 or 8 things in the same number of clock cycles. So what do I mean by exploit? Well, I want to use these things, and in particular, I want to make it easy to use from a high-level approach. So let me give you a short example in Haskell. It fits on a slide. So it's called .p, and I've called it .p in the Haskell notation. It's really d.p in the BLAS. That's the BLAS routine thing. So BLAS is the basic linear algebra system. Been around for decades. It's a library for doing kind of vector matrix operations. And d.p is the double precision version of the dot product. So if you're familiar with MATLAB, probably more people are familiar with MATLAB than Haskell in the room. And safely, I think it's safe to say the rest of the world. So here's the MATLAB implementation of dot product. So just multiply these two vectors pairwise. That's kind of this v zip width, right? So I'm zipping down these two vectors, applying this multiplication operator to each element. So applying that operator pairwise. And then I'm just summing things up. So this fold, it says, you know, okay, it takes an associative operator, it takes the unit, blah, blah, blah. It's just sum. So looking at this MATLAB code, how many vectors does it create? Think about the implementation. So MATLAB's running this code. How many vectors does it consume? 2. How many vectors do you think it produces? Well, at least one. At least one. But okay, here's an operation, multiplying these things pairwise. I would expect that to produce a vector that contains kind of the multiplied elements. And then what's this sum guy doing? Well, the sum is going to consume this vector and produce a result. So I expect this code is producing one vector inside, some intermediate vector. Now, you know what dot product does. If you were implementing this in C, how many intermediate vectors would your code produce? Hopefully 0, right? Yeah, well, I mean, this is silly, right? You just multiply these guys together and then add them up. You don't need to manifest them anywhere, right? And in fact, this code, the Haskell code, doesn't manifest an intermediate vector. I'll show you the assembly that comes out. But we can still write these things in this nice compositional way. Now, for dot product, maybe it doesn't matter so much. But think about larger programs. You like these kind of operations to fuse together. So we call this fusion, where you kind of eliminate these intermediate structures. We like these operations to fuse together in general. We don't have to do that manually by hand. So using this library that I implemented in Haskell, you get that fusion for free. So the compiler does that, the compiler library does that for you. So I can write these guys, even in completely different places, completely different libraries. I could write this zip width and this fold, 2 different places. And when you use them in a compositional way in your own code, fusion occurs. The code is fused together when you use it. So let me show you the performance here. So performance comparison with a number of different implementations. So I've marked, working set in bytes, the L1, L2, and L3 cache here. So this really high curve is actually go-to BLAS. So this is a guy who spent much of his life, many years of his life, hand-tuning BLAS routines. These were processor-specific implementations written in assembly language by hand. So this was his job. He worked at UT Austin for a while doing this, then he went to Microsoft and Intel, and I don't know where he is now. But so this was his life's work, was creating these tuned implementations. So certainly fast, right? So where is the Haskell implementation? So this is the purple dot here is the vector library. This is the library implemented using SSE instructions. And here it is. Right? So it's actually pretty competitive with handwritten C, and even handwritten C that utilizes SSE intrinsics. So the goal here isn't to beat the C compilers, it's to be competitive. I think we can safely say that we are competitive. Maybe when I show you the assembly language, you'll finally agree with me if you don't now. So this is actually the loop that comes out of that. This is the loop that comes out of exactly the code I showed you before. There's no memory allocation here. I'm using vector instructions. In fact, I'm prefetching. I'm doing loop unrolling. So all this stuff is inside that library. You get it for free, even though you use this nice high-level code. So you can write your nice high-level code in this compositional way. You get Fusion for free. You eliminate all these intermediate structures. You use these nice low-level SSE intrinsics, all from high-level code. So this is just a brief taste of what the library does. So there are more, if you want to read the paper, there's more benchmarks, including comparisons with some C++ matrix libraries. You can use bulk memory operations on vectors. That's another optimization does. There's a certain representation that we use internally that allows this kind of fusion to occur. Details in the paper. You can transparently use, so use of SIMD instructions is not quite transparent in the code I showed you. You have to use these special versions of fold and multiply zip width. But if you use a system called data parallel Haskell, in that case, the Haskell compiler actually vectorizes the code for you and translates that vectorized code to use the SIMD instructions automatically. So you have to rewrite a little bit, just a little bit of your code to use the SIMD instructions just using the clinical vector library. If you use data parallel Haskell, you don't even have to do that. It all comes for free. And I haven't talked about the loop unrolling or prefetching at all, so that's discussed in the paper. And there weren't actually any compiler modifications that we needed to do this. So I added intrinsics, so SSE intrinsics to the compiler, those basic SSE instructions. But the rest of it was just the library, taking advantage of compiler optimization. So GHC happens to be have a great optimizer, so we could really leverage that and do all of this without modifying the compiler itself. It's all done in the library. So let me move on. Hopefully I've convinced you that we can get good performance out of this high-level code, and move on to talking about programming these devices, GPUs. So this is my Tesla K20 again. The goal here is to compile a subset of Haskell to GPU binary code. So this isn't, they call these GPUs, general purpose GPUs, but they're not really general purpose. You still have to tailor your problem for the device, or your problem has to be tailored for the device. You can't just take any program and compile it for GPU. So we're going to carve out a subset of Haskell that we know we can compile efficiently to GPUs, and compile that. So we're giving you the guarantee as a programmer, as long as you write in our subset, we can do a good job compiling to GPUs. If you've done any CUDA programming, any GPU programming, you know that you have to manually handle transferring data back and forth between the CPU and GPU. So they don't really have a shared memory space yet. So you have to make sure that the data that you're computing with makes it from the CPU to GPU. So you can then operate it on the GPU, and then you have to move it back to the GPU to do something better. Nicola takes care of all that for you. And again, it doesn't actually require any compiler modifications, and there's no runtime code generation here. So we're adding kind of GPU binary code to Haskell without modifying the compiler. And it's implemented as an embedded domain-specific language. So I mentioned earlier, one of the things that's nice about Haskell is that you can do these embedded languages, and we leveraged that here. So I won't talk about it, but that was something that really helped us implement the system. So let me give you another example of some Haskell code. And this is code that runs on the GPU. So it's just Sobel edge detection. Again, if you don't know Haskell, it's fine. We'll just walk through it. So this is just a type alias. So I'm keeping a Luma channel, luminescence channel. So this is just an array. It's a two-dimensional array, and it holds some double precision floating point stuff. Then I'm going to define two operators. And so here's my type signature. So it takes a Luma channel, luminescence channel, produces a new luminescence channel. What is it going to do? So this is the Sobel operating in the X direction. It's just a convolution. And here's my convolution kernel. So what am I doing here? Well, I'm kind of taking I'm taking an input image and taking some values around each pixel in my input image and mapping them out onto a pixel in my output image using this kernel. So you can think of this as, here's my output pixel in the middle, and I've got to go to my source image, and it's going to tell me how I compute that output pixel. So I have this little 3x3 grid in my source image, and I'm kind of taking this gradient. So this is doing edge detection. So here I'm kind of taking this gradient in the x direction. So that's my gradient, my Sobel x operator. And here I'm taking the gradient in the y direction. So I'm kind of getting the y direction and the x direction independently. And then I'm combining them just using the L2 norm. So here I'm computing x and y, computing the L2 norm, and that's my final output, right? So again, if you look at this, well, it looks like I'm creating a bunch of intermediate stuff here. I've written these operators separately, my x and y operators. They're both taking some inputs, matrix values, and producing an output matrix. And then I'm taking those two outputs and recombining them to produce my final value. So it looks like producing two intermediate things here. As you might imagine, that's not actually happening, so you can have happening in the implementation. So you can write this nice high-level code in this compositional style, where you don't have to manually fuse these operations together, and the compiler will fuse them together for you. So let me show you the kind of CUDA output here. So this is the Haskell code. This is the CUDA code. So actually the Sobel stuff is here. This is a separate function that takes data in from a webcam, does some color conversion, translates the image, etc. This is doing the Sobel and doing some interpolation, so it's loading up the image. Now, unfortunately, my laptop doesn't have an NVIDIA processor, so I can't show you a live demo, but I can show you a screen capture. So this is just looping. So this is just that program running in a loop on a webcam. So you can see it's real-time, high-level Haskell code, and this is actually what comes out of the system. So it's pretty efficient. Okay. So let me move on to software-defined radio. I think this is joint work, people at MSR and various other places. So this is my Sora radio control board. This is a similar device, a USRP B200, both software-defined radio platforms. As I mentioned, they're great for research and development because they let you define these new protocols in software. So you don't have to go write Verilog or, even worse, go burn a custom chip to test these things. You just do it in software. Now the disadvantage is that platforms like New Radio, which is what you would use to program the USRP B200, are actually fairly slow. So you can't do high-speed line rate stuff with New Radio. Or they require really hand-tuned code. So Sora, this does have a software implementation of line rate 802.11, for example, but it's very carefully tuned. So if you wanted to go modify that implementation, you'd kind of be out of luck. So the paper demonstrates that software implementations are possible, but it doesn't demonstrate, the original Sora paper, it doesn't demonstrate that you can do this easily and modify implementation and still get a line rate implementation. So this language Blink that we've developed is tailored to these software-defined radio tasks, but the goal is to let you change your program very easily and still get an efficient implementation. And we've done that by comparing an implementation of 802.11 in Blink with the original Sora implementation and demonstrating that you can get line rate code out of Blink. It's still very high level. So let me just give a small excerpt of this Blink code. So this is the scrambler from 802.11. So what the scrambler does is, so maybe it makes sense intuitively in 802.11 in any kind of signal processing program. You don't want lots of ones and zeros, and long strings of ones and zeros. It's not very good because it's hard to discriminate between the different values. So typically you have some sort of scrambling phase, just exclusive OR with some deterministic bit generator so that you get something that looks random. It makes it easier to differentiate the different bits from each other because they're not all the same. So that's all this is doing. And this is in fact a pretty straightforward translation from the 802.11 spec. Again, don't worry about the implementation here, but we have some state here, some bits, so this is a bit array. So we're taking a value from our inputs, we're doing some operations exclusive OR and shifting some bits around, and then emitting the output. So this is a pretty faithful translation from the spec. If you go look at the Sora implementation, any guesses as to how that implementation is written? Do you think it's written in a loop like this? Probably not. It's written using a lookup table, a static lookup table. So instead of a loop, they have kind of partially evaluated this thing or memo-wized it. So you give me some string of bits, and I go look in a giant table to figure out what the output should be. How painful do you think it would be to change that implementation? You have to go regenerate that lookup table. Right? So one thing I worked on in this compiler is automatically finding places where you can convert these expressions or functions to use lookup tables, and then generating lookup tables. So you can write this code, and you still get a lookup implementation out of the system. So you get something similar to what Sora would provide, but you've written this nice high-level code instead. So it's automatically taken care of for you by the compiler. Now, unfortunately, we're not as fast as Sora. I think that's to be expected because the Sora guys spend a lot of time hand-tuning their implementation. But we're not bad. So these are benchmarks for various transmission rates. So this is the Sora transmission rate. So this MD per second is kind of megs of data unit per second. It turns out that the rate doesn't depend so much on the width of the individual things that you're pushing through the system. So we include this measurement instead. This is the kind of optimized version throughput. And this is what the spec requires. So we meet the spec. We're not as fast as Sora, but at least we meet the spec, and usually with quite a bit of room. And these are the numbers for compiled implementations that don't use optimization. So there are two optimizations, main optimizations here. One is this vectorization, and one is this LUT table lookup that I implemented. So you can see without those implementations, without those optimizations, we're not doing so well. And when you add them both in, pretty fast. So why can we actually do this with link code? Because it's tailored to the domain. If this were just written in C, you wouldn't have much hope of performing these sorts of optimizations. But when you have a language that's tailored to the domain, where the compiler can figure out a lot about the program just from looking at the program itself, you can perform these sorts of optimizations. And that really lets you leverage these high-level languages and still get efficient level code. So what do we still have to do? Well, we actually have an interface to link with the hardware itself. So that's still future work. So getting to run that on these actual hardware platforms. It would be nice to get to run more than one hardware platform. So not only on the Sora board, but also on this USRP, for example. Right now, we're just compiling to C. If you looked at the Sora board, I think I mentioned there's actually an FPGA on there. It would be nice to be able to compile this stuff to FPGAs, get even better performance out of it. And it seems plausible, and then we have this high-level language, we're translating to C. Why not translate the same thing down to Verilog and compile it for these FPGAs? I'm kind of interested in doing just a Haskell comparison with a Haskell embedding. So you'll notice that it wasn't Haskell code, that was Blink code, so it's a completely different language. Gordon, who implemented the parser, I said, go look at this stuff. It tells you how to do these Haskell embeddings, and he hadn't really done much Haskell before, so he kind of poo-pooed it. But then a few weeks ago, he said to me, I was looking at that stuff, and I think it would have been actually much easier to do a Haskell embedding. So that'd be kind of interesting to do, just to compare the pain of the Haskell embedding to the pain of this full-on implementation. And finally, real goal, longer term, is to implement LTE, a much more demanding protocol. So can we take a protocol that's LTE and implement that into the system? So we've seen software-defined radio. Now how about software-defined networking? So this is this net FPGA that I've shown you before. What is the point behind software-defined networking? Well, the goal is really to separate the control plane from the data plane. So the data plane is where all the packets are being transmitted. The packets are going through the data plane. The control plane is controlling where the packets go. So we kind of like to write a single program, single control program that determines routing decisions for the entire network. So let's say that I'm a big company, I have a zillion routers, I have some network security policy that I want to impose on the system. How do I do that? I have 100 routers. How can I be assured that the policy that I want to impose in the system is actually correctly implemented? How do I reason about that? So software-defined networking goal is to be able to do that kind of programming. So you can take this nice high-level specification of what the network as a whole should be doing and push it onto the system. Now the current focus in this area is on something called OpenFlow protocol, and software for central controllers. So the way OpenFlow works is the routers themselves are still pretty dumb. They have tables that tell them what to do with packets. If there's an exception, so something strange happens that doesn't know how to handle, it sends the packet itself all the way to the central controller, which is typically a beefy CPU. And then the CPU will make some decision about the packet and potentially drop it, or maybe even send it back to a different router and say, okay, now you handle this packet, this is what you should do with it. A lot of latency involved in these kinds of round trips. If you're sending a packet from a router all the way to some CPU, and the CPU has to process it, you're incurring a pretty significant time penalty. Again, these devices have FPGAs on them. Pretty beefy computational unit, not good for general purpose computation, but it seems like we should be able to leverage this to push a lot of that stuff that's going on at the centralized controller back to the edge of the network and avoid those long latencies. So that's the kind of thing I want to work on, is expand the existing work on leveraging things like OpenFlow for controlling networks and figuring out what kind of abstractions we need to push that computation that's now occurring on these CPUs back into the network. So other things I'm interested in, so data flattening for parallelism. There's this interesting language you may have heard of called Nestle. It came out of CMU about 20 years ago. And the goal with Nestle was to take nested data parallel programs. So what's a flat data parallel program, first of all? A flat data parallel program is, okay, I have a vector of stuff, I'm going to do the same thing with every element of the vector. That's a pretty good model for things like vector computers like the Cray, which was the big vector computer back when Nestle was developed, even for platforms like GPUs today. Let's say that I want to operate on something that's not flat, though, that has, say, a tree structure. Well, then I'm out of luck, right, with these kind of vector computers. So Nestle has this data flattening technique that lets you transform these nested data parallel computations into flat data parallel computations. It turns out, I think at least it turns out, that you actually want some control over how this flattening occurs, and you can get big performance benefits by allowing the programmer potentially to control how the flattening is actually implemented. That's one thing I'm interested in working on. Nested loops are always a problem. So this kind of language, Nicola, for performing these array computations doesn't handle nested loops very well. So we do have some good tools for that in the programming language community, polyhedra model. So I'm interested in applying the polyhedra model to these nested loop computations and seeing if we can leverage that to get good performance, even better performance from this high-level code. So kind of unrelated, in the machine learning domain, I'm interested in performing inference on generative models. So the idea here is that I write some generative model. So what's generative means I have some model, I think this is what's happening in the system. So I write a program that's going to generate data, so sample data points from some data set, from this distribution that I think exists, right? So I know what the distribution is, but I can write a program that will generate samples of the distribution. Now I'd like to find out what the distribution is. So I kind of want to run it in reverse. So Markov chain Monte Carlo is one technique for finding distributions when you have these sort of generative things. So I'm interested in general of running these generative models in reverse using PL techniques. I haven't talked about metaprogramming at all. So metaprogramming is writing programs that construct programs. So I've done some work in that area. I'm interested generally in better language support for metaprogramming, so better language support for writing programs that generate programs. So Nicola is an instance of this, right? We're generating CUDA code. Blink generates C code. Also interested in better tools for these language embeddings. And finally, if your type system is interested in programmable type systems, these two kind of tie into each other. So with that, I'm happy to take questions.
Thank you. Questions?
Can you go back to the performance plot slide? where you compare your code?
This one?
No, the one with the performance part. So I wonder, where did you get the handwritten C?
I just wrote it.
Okay, so it's not from like a vendor libraries like
No. The Goto Blast is vendor library. So that was kind of, if you could find the most highly tuned version possible, that was it.
Okay.
That was the idea.
So
the idea behind the handwritten C was that, if I wanted to go write something, if I wanted to implement it myself, and I was concerned about performance, I just go write it in C. I wouldn't use a high-level language. Right. So that was the comparison I wanted to do there. So what would a usual programmer, if they want to go implement something by hand to get performance, what tool would they use, and how does that compare with the high-level implementation? So that was the motivation.
Okay. So how general is your automatic vectorization can provide? From this very low-level function, do you also see like a similar speed up on like a higher level?
So it doesn't actually automatically vectorize things. It lets you tie together things that have been vectorized and eliminate these intermediate data structures. If you use something like DPH, that does the vectorization. Then you get the vectorization and the fusion. This was really just a way to do the fusion. So you can still write high-level code that it doesn't actually vectorize it for you, but it makes it easy to write the vectorized code. So again, nested loops are a problem, but it does operate fairly. It is fairly general otherwise.
Okay. Thank you.
Does your code, the handwritten C, do exactly what the assembly code does?
No.
No. It's a different approach to doing it, correct?
Yeah.
So this is not sort of the effect of C compilers having really good optimization algorithms to generate assembly code that runs faster on the target machine. Because this blast code, the first graph, might have been hand optimized for a specific architecture.
Yep.
So
yeah, that was hand optimized for a specific architecture.
Did you run your experiments on that architecture?
On the most similar architecture I could find, because Goto Blast has not been updated for recent Intel processors.
Right. Okay.
Any other questions?
Sorry. How similar are the how much work has to be done when you get like a new GPU or a new piece of hardware to make these types of things work for them? Like how?
It depends on, for example, does NVIDIA let you compile the same CUDA code identical CUDA code to the new hardware and doesn't perform the same? That's generally true. But what's not the case, for example, is if I were writing OpenScale, which is another language similar to CUDA, but it's supposed to be cross-platform. I wrote an OpenCL program. I tuned it for NVIDIA's architecture. It's not going to run the same on AMD's architecture. So that kind of code needs to be rewritten. What I'm kind of arguing for is that I'd like to be able to do that rewriting once. So use something like Nicola. I figure out what the target-specific optimizations need to be. You write in a nice high-level way, and then you get to reuse that knowledge time and time again. You don't have to learn it yourself. So taking that from a kind of n by m thing to just an in order in thing. Right? So you write in programs. Well, and I need to go perform these optimizations on each program given the architecture. Really, I just take my in programs. I go add a new back end to my nice high-level language and perform all those optimizations on that. So that's the point. You still have to do the work somewhere.
Yeah.
But I'd like to commoditize that work.
Yeah. In the back of my mind, kind of a fun experimental platform for this kind of work might be to play around with Bitcoin mining or some other type of cryptocurrency. Have you thought about?
I think that's that's an interesting application, and in particular, can you
do close to? Then you can measure your effects in dollars as opposed to.
Well, okay. I'm an academia. I don't think about dollars that much, right? Let's not write grant proposals, but I think getting an FPGA implementation is something like Bitcoin mining. I actually have wondered about that specifically.
Right.
It's a really, really interesting to work on. So if there are any students who are interested in this kind of stuff, please let me know.
And,
Yeah, Can you give an example of using this kind of code for machine learning?
No.
No.
I can't. I mean, I can't give an example I've done. I can give you an example of existing work.
Mm-hmm.
This is something I'm interested in moving into, but I haven't started on yet.
Okay.
So,
What has been done by other people?
so people have done this kind of inference. So there's a language called Church, which came out of MIT. It's based on Lisp. So they do this kind of Markov chain Monte Carlo. You write this program, they do this MC inference, and so that's been around for, I don't know, 10 years or so. It's not very efficient. So the challenge is getting efficient inference out of these systems. So maybe you don't want to use Markov chain Monte Carlo. It's a very general technique. Maybe you can use knowledge about the program. So maybe types tell you something that lets you implement a more efficient version of inference. So if you have a just general language, general purpose language, untyped like Lisp, maybe you're stuck just doing MC, just using general purpose algorithm. Maybe you can take advantage of more domain-specific knowledge and things like type systems to implement more efficient inference. So that's the kind of question I'm interested
Okay.
So the SDN stuff that you're doing, I remember talking to you a bit about this. I don't know a whole lot about it, but I was under the impression that separating the control plane from the data plane helped reduce the management complexity. And I've heard a lot of people champion this on YouTube videos and so forth. And the idea of having sort of stupid hardware and centralizing all that control and the controller at the top. But it sounds like you're advocating putting a little bit of intelligence into the bottom layer. And I'm just wondering, philosophically, how much stuff do you think is safe to put in there from a management point of view?
So why do people move the smarts back to a centralized controller? That's the question. What makes it easier? Because if you move it back to the centralized controller, it's in one place. It's easier to reason about, right? You have one program on one machine. That's where your smarts are. What if I gave you a high-level language? You could reason about that language as if it were running on centralized controller, but it's actually distributed. So that's the goal. You can still write your program and reason about it as if it's running in a central place, as if it sees all the packets. But it doesn't actually see all the packets. It's decomposed into individual bits that don't see all the packets and run on distributed routers. So it looks like your program is centralized controller, but you're not. That's the goal.
Cool. Thank you.
All right, well, thank our speaker one more time.